So, so hello everyone, welcome back to the second session of the event. So the second session consists of student talks. So each talk will be about 10 minutes and we have 5 talks, and this will be followed by the poster presentation by some time for people to look at the posters. So the first talk will be by Andela Sarkovic, and she will talk to us about cutoff for random walk on the 2 communities random graph. So Andela.
Yeah, so I will be talking about my recent work with my supervisor Perla Susi and with collaborator Jonathan Herman. So first, to motivate our work, let me just define what do we mean by the community structure. So community structure simply means that when we take our graph, we can divide vertices into more groups such that the vertices which are in the same group are more likely to be connected than the vertices which are in the different group. And then when you look on some random graph models, for example, a deregular random graph, you actually with high probability don't get this community structure. But interestingly enough, when you look on many real world graphs, you do get that the community structure appears. So just some example would be social networks like acquaintance networks or collaboration networks, and then technological networks as well, like internet and power grid, and then biological networks as well. Like, as it says, neural networks, food webs, and metabolic networks. So that's why people are interested in studying this graph, which shows some community structure. And we actually restricted ourselves to the 2 communities graph for the start, but we are convinced that our result actually generalizes to the graph with more communities, and we are currently working on that. So what we actually have is that we take a random graph with 2 communities in the following way. So we first fix n, and we choose n vertices, and we split them into communities such that they're of approximately same size. And then we choose degree for each of the vertex. So on this picture here, I've chosen that the degree for each vertex is 3. But we can choose it to be any degree, which is bounded by some constant delta. And then we choose the number of edges which will go across the 2 communities, and we can choose this as a function of n. And for example, it's 6 here. And then we connect this uniformly at random, which just means that we take one graph out of all the graphs which satisfy these constraints. So the number, so the degree of each vertex and the number of edges across the 2 communities. And then we are curious what will be the geometry of this graph in some sense when we take this random sample generated like this. And one standard way to study it is to actually study how the random walk on such a graph behaves. So a simple random walk will just be a walk which moves from vertex u to any of its neighbors v with equal probability, so 1 over the degree of u. And then it is a well-known result that as t goes to infinity, this random walk will converge to invariant distribution, which will just be this degree biased distribution. So naturally, when you think about it, when you wait a long time, you would expect your walk to be equally likely anywhere, but you would also expect it to be slightly more likely at the vertices of higher degree because it has more opportunities to reach them throughout more other vertices. And this is just a well-known result, but the way you can study this convergence a bit better is by studying how fast it happens. So therefore, we define a mixing time. So first, we just use a total variation distance as a notion of distances between the 2 distributions. And then we say, okay, we maximize over any starting vertex the distance between our walk at time t and this invariant distribution. And then we say that the epsilon mixing time, this t mix of epsilon, is just the first time when this dt, which we define as this maximum overall v of the distance of our walk at time t and the invariant distribution. So the first time when this dt drops below epsilon. And when you study the mixing times, one very interesting phenomenon that happens is a cutoff phenomenon. So first it was noticed by Percy Diakonos when he studied card shufflings. So what he noticed is if you take the deck of 52 cards and you shuffle it in the standard way as they do in casinos, when you do 5 shuffles, the way the cards are distributed is very dependent on the way they were distributed in the start, so on the initial order of cards. But when you do 7 shuffles, they will actually be very well shuffled, and you couldn't say by knowing the initial order where your card will be. So if you take n cards around time constant times n log n, your deck, for some constant that you can find depending on the shuffle you do, your deck will go very quickly from being not very well shuffled to being very well shuffled. So basically this phenomenon of cutoff is the phenomenon that your dn of t, which was this distance between the invariant distribution and the your Markov chain at time t, will drop very quickly from 1 to 0 around this mixing time. So it can actually be defined that it happens if the mixing time of order epsilon is approximately the same as mixing time of order 1 minus epsilon for any epsilon close to 0. And what we noticed is that actually on the random graph model that we looked on, the cutoff will appear in some cases. So first of all, the mixing time of our model is of order log n. And then we noticed that if the proportion of the edges, which goes across the two communities, is somehow greater than 1 over log n, the random walk will exhibit a cutoff. While if it is smaller than 1 over log n, then with high probability, there is no cutoff. So this actually suggests some change in the geometry of the graph when these thresholds go below log n. So what's interesting is that the proportion of edges can go to 0 still, which go across the two communities, can go to 0 still, right? So if we take a function 1 divided by root log n, for example, and there will be some obvious community structure in that case, but we would still have somehow similar geometry of the graph to the random graph, which is taken with to have no communities. But if this is dropped below 1 over log n, then the geometry somehow changes. So this is some threshold value, which suggests that the graph is very different when you take less than that edges across the two communities. And our work is also important because actually there are many graphs on which it was shown that random walks do exhibit a cutoff, but there was actually no easy condition discovered yet when the cutoff would hold. And many conditions that were conjectured were proven to actually be false. So we are hoping that by investigating more graphs and more cases in which cutoff hold, we could get closer to solving this question of how you could classify whether a cutoff for some Markov chain holds or not. So thank you for your attention. Do you have any questions?
Okay, thanks a lot, Andela. That was very good on time. So any questions from the audience for Andela? So, okay, I actually have a question. Maybe I can start. So, I mean, on this slide, when you say the mixing time is a further log n, so this does, okay, so actually two questions. What is this for a fixed epsilon or? Hello?
Yeah, so if we take epsilon to be 1/4,
okay,
for example, then it will be some constant times log n. But
I can hear you. Yeah, I can hear you. Sorry, I've got the Zoom playing here. 1 second.
okay, so we have a problem with the Zoom here. 1 second. I don't know. Probably someone at Gather Town.
There is an echo somehow.
Yeah. Sorry. So Andela, yeah, can you?
Yeah, so if we take epsilon to be 1/4, we showed that it's a constant times log n, but because in this regime, when we have over 1 over log n vertices, edges across the two communities, we showed cutoff. That means that even if we take any small epsilon, it will be around that C log n. So we show actually that there is a window which is of order root log n times some constant, and that around that window from log n, C log n minus some other constant times root log n to C log n plus some other constant root log n, it will go from not being mixed at all to being very, very well mixed.
Oh, I see.
So it's the same constant log n for any epsilon, basically.
So this is just to make sure. I mean, your model, the degree is fixed. I mean, it's the degree of all the nodes is constant, right? It's the same.
Yeah, so that's how we choose the model. But we just take some universal constant delta,
Okay.
and we only want our degrees not to be above that delta because of some things we use. Though we believe that you could even take degrees to go to infinity somehow, but we are not yet sure whether that would hold. But then we can choose the degrees for any vertex in any way we want, just to be bounded by delta.
Okay. Okay, thanks a lot, Andela. That was really nice and very interesting. So now